A rectangular equation is an equation like, like y equals 2x plus 5. Basically, an equation that has an x and a y in it, and it's something we're able to make a graph out of, where every point on the graph corresponds to an x and a y that makes the equation true. A polar equation is an equation that somehow has r and theta involved in it, and we can find solutions to that equation that help us create a graph with polar coordinates. And I'm going to take you through some examples by comparing what an equation would be for a graph in rectangular versus a graph for polar. And I think I'd like to put these on the same page. So just to show you how two equations could look very similar, like y equals x over 90. If I were to make a little xy chart to find ordered pairs, 0, 90, 180, 270, 360, would get 0, 1, 2, 3, 4. And if I graphed it, I would get a very flattish line. R equals theta over 90. If I were to make an r theta chart for that, actually I'll say theta r, and did the same sort of four ideas, 180, 270, 360, 0, 1, 2, 3, 4. If I graph those points, remember we graph r first and then theta, or we write the points as 0, 0, wouldn't matter in this case, but this one would be 1, 90. So the second point would look like this, and the third one would be 2, 180, which is out here, and the third one, and the next point is 3, 270, which is over here, and the next one is 4, 360, which would be over here. So if I connected the dots, it actually turns into a spiral. So what we see here are two equations that resemble each other, but if I interpret them as points on the rectangular, it makes one picture, and if I think of them as polar coordinates, I get a totally different picture. Now let's look at some famous polar graphs. Well, here's a circle with radius 5. And in rectangular, it's x squared plus y squared equals 25, which is a fairly complicated equation. But for polar, the equation would be r equals 5, and I'm going to show you why that is. So I have theta and r, and if I do 0, I get 5, because r equals 5. No, but theta's not even in here. 90 gets me 5. 180 becomes 5. Anything, 1 gets me 5. So when I graph all those points, I end up with the same circle. So an equation that's kind of complicated in rectangular, x squared plus y squared equals 25, is much simpler to describe in polar with the equation r equals 5. And that's the equation of a circle centered at the pole, which is also 0, 0. The equation for a circle is very easy. It's just r equals whatever the radius of the circle is. Now you could convert equations. Like if you know the equation in polar, you could turn it into a rectangular equation, and vice versa. Show you how to do that. Let me remind you of the relationships. The relationships are r squared equals x squared plus y squared, and tan theta equals absolute value of y over absolute value of x, and x equals r cosine theta, and y equals r cosine. Those are like the relationships. So now I get an equation like r equals theta, like r equals 5. And I have an equation for r squared, so if I square both sides, I get r squared equals 25, and then I replace r squared with x squared plus y squared, and I get x squared plus y squared equals 25. I could also go in the opposite direction. If I started with x squared plus y squared equals 25, and I have this rule here, I could change it to r squared equals 25 or r equals 5. I'm not going to do plus minus because it's fine to just do it that way. And we can go backwards. If we notice we have a circle centered at 0, 0, the equation, we could figure out the equation. This is like, I'd have to tell you, it's a little confusing to see that, but this is r equals 7. It's a circle with radius 7. Maybe they give you a point on it, 7 comma 0 degrees. I don't know what that is. That's really number 7. Okay, the next graph I want to show you, so we've done circle centered at 0, 0. How about a line? Well, here's an equation, theta equals 30 degrees. So for this one, no matter what r is, 2, 1, 0, minus 1, 5, whatever, theta is going to be 30 degrees. And when you graph all of those, what you end up with are points on the 30 degree. And if you have negatives here, it's going to be points over there. Either way, it turns into a line that goes through 0, 0. Now, if you wanted to change this equation into rectangular, we would say theta equals 30. And we have this sort of list of relationships. One of the only one that's we have this theta here. So if I take the tan of both sides, I get tan theta equals tan 30. But tan theta can be replaced with absolute value of y over absolute value of x, and tan 30 can be replaced with 1 over radical 3, and we get y equals 1 over radical 3x. So this is a line with a slope of 1 over radical 3. We could go in the other direction. If I started with y equals 1 over radical 3x, I could divide both sides by x. And then we have the rule that one of these rules is that tan inverse is y over x. So I can replace this with tan theta equals 1 over radical 3. And then I could do the tan inverse of both sides. And I would get theta is equal to 30 degrees. Now in rectangular, if we have a line that goes through 0, 0, it's going to be y equals something x, depending on what the slope is. One way that we can find the equation of a line in rectangular, you pick a random point on it. We do this with parabolas actually. You call it xy. And then we try to make a relationship with x and y. And in this case, this is a sort of new idea. If I draw these vertical lines, I see I have a little... I have similar triangles here, and this is x and y are also the lengths of this and that. So because of similar triangles, I can say y over x is equal to 1 over square root of 3, and if I multiply both sides, so that's a kind of a way to create a graph. There's other ways to get this one. Certainly if it goes through 0, 0, we'd know that the slope is 1 over radical 3, and its y-intercept is 0. In polar, it's a lot easier. When I see this straight line going through 0, 0, I could just jump and say, okay, every point on this line has in common theta equals 30, and that one's all finished. Okay, so now we've done a circle with center at 0, 0, and a line that passes through 0, 0. But these get more complicated. Look at this equation. R equals 5 over sine theta. So that's a complicated looking equation, and you might expect it to have a complicated graph. But the graph is actually not going to be that complicated. If I go 0, 90, 180, and 270, if I try to do those 4 points, well, sine of 0 is 0, so 5 over would be undefined. 90 would become 5. 180 is undefined again, and 270 becomes negative 5. So that's not so good. I have 2 points, 95, which is over here somewhere, and 270 negative 5, which is also over there. So that's not so useful. So why don't I throw in another couple of points? If I do 30, sine of 30 is 1/2. 5 over 1/2 is 10. So 30, 10, somewhere over there. And if I do 45, I end up with about 7.1, which ends up about over here. And it turns out that if I do all the points in a rectangular, a polar equation like this actually produces a horizontal line. In rectangular, it would be the line y equals 5. So here's an example where the rectangular equation for the thing is much simpler than the polar equation for the same thing. If you wanted to use these rules to find to convert, watch what we would do. 5 equals 5 over sine theta. Cross multiply r sine theta equals 5. Look at these rules. One of the rules is r sine theta is the same thing as y, so y equals 5. So that's how you can convert that way. And actually you can go in the other direction also. If you knew y equals 5, the rule here says that y is equal to r sine theta. So r sine theta is equal to 5. Then divide both sides by sine theta. Usually we want r to be the independent variable, kind of like y is usually the independent variable when we have like y equals mx plus b or things like that. That way we can make theta our independent variable and plug in different values of theta to get different values of r's. If you have this equation already and you didn't know this, well, it'll be real easy to say y equals 5, because every point on here is a y coordinate of 5. But if you saw the line y equals 5 in polar, I want to show you like a strategy, and this strategy is going to get used for much more complicated things coming up. Imagine I didn't even know this. I just wanted the equation in polar. For this one, it's real easy. For rectangular xy, well, of course, every point on it has y equals 5. But for this one, it's kind of complicated. So the trick is, and this is a difficult idea, we call a random point on this line r comma theta. Then I can make this line here and call this line segment this r, and I can make a right triangle and put theta here. And we know this number is 5 because this line is y equals 5, so this distance is going to be 5. And then I look at this triangle and make a relationship. The 5 is the opposite and the r is the hypotenuse, so I can say that sine theta equals 5 over r, which is, this is an answer, but it's better to multiply both sides by r and divide both sides by sine theta. A vertical line, like this one over here, well, that's x equals 5 in rectangular, but it's not in polar. It's got a much more complicated equation. If I pick a random point here and call this r comma theta, and this is r and that's theta, and this is 5, the relationship between these three things would be, because 5 is the adjacent to the theta, it would be cosine theta equals 5 over r, or r equals 5 over cosine theta. So for a vertical line, it's r equals 5, or whatever it is, over cosine, and for a horizontal line, it's whatever the number is, over sine. We could verify these. R equals 5 over cosine theta, convert it to rectangular by cross multiplying. And one of these rules here is x equals r cosine theta. So x equals 5. I could also go the other way around. If I had x equals 5, I could say r cosine theta equals 5, or r equals 5 over cosine theta. So what we've done in this lecture is look at the equation of a circle in polar, of a line through the origin in polar, of a vertical line in polar, and a horizontal line in polar, and looked at their various equations and how we could calculate them.